10, 9, 8, 7. We have a go.
The FAA is
command
already
start.
planning to
5,
transition from a
4,
land-based navigational
3,
system
2,
to GPS
1,
as the primary
and
navigational
liftoff.
system of the future.
Pilots like GPS because their confidence level in GPS is very high.
The pilot will have a database of every fix in the National Airspace System, so there won't be any question that the pilot knows exactly where you want him to go.
GPS technology is revolutionizing the entire transportation industry. And as air traffic controllers, you are at the center of that change. So you need to know about GPS and how GPS will affect the National Airspace System. The Global Positioning System is an extremely precise navigation system, initially developed and operated by the U.S. Department of Defense, that is now available for civilian use. GPS consists of a system of satellites, ground-based stations, and aircraft-based receivers. GPS provides precise, continuous navigational data that is unaffected by weather, terrain, or time of day.
As more airplanes equipped with GPS, the controller will have more flexibility to reroute aircraft around weather, around heavily congested areas, to benefit not only the user but the controller.
GPS users receive precise position and velocity data and very precise time. And GPS can serve an unlimited number of users in aviation, maritime, and surface vehicles. The Global Positioning System will revolutionize the National Airspace System. GPS is rapidly becoming an integral component of the NAS and will improve NAS capabilities dramatically in the coming years. GPS may eventually replace much of the current ground-based system of navigational aids, such as VOR systems. GPS approaches are currently being added throughout the NAS, and GPS can eventually provide approaches to all airports and heliports, regardless of location.
Since GPS isn't tied to any ground-based nav aids, the airspace can be used in the most efficient way. We can design procedures to put the airplanes right where they want to be and where we need them to be to keep everybody moving.
The en route environment will also benefit. Aircraft will no longer be restricted to routes based on ground-dependent nav aids. GPS will allow controllers to put routes where they're needed, so controllers can provide pilots with optimum routings. GPS is truly a revolution in navigational technology, and it will affect everybody, especially the aviation industry. Let's look at the individual components of GPS and how the system operates. The satellite component of the Global Positioning System consists of 24 GPS satellites orbiting 10,900 nautical miles above the Earth. The satellites are deployed in 6 orbital planes containing 4 satellites each. Each satellite orbits the Earth every 11 hours and 58 minutes and transmits a unique coded signal consisting of the satellite's identification and current position, precise time, and clock bias or error, if any. The accuracy of the time element of the GPS signal is essential to making a precise position calculation. A timing error of as little as 1/100th of a second would result in an error in the position calculation of 1,860 miles, so the satellites base their timing on atomic clocks, accurate to 1 nanosecond. The Global Positioning System is monitored and controlled by the Department of Defense to ensure the accuracy of the navigational signals. 5 monitor stations located throughout the world receive GPS signals from the satellites. The monitor stations collect clock and position data and transmit the collected data to the Master Control Station in Colorado Springs every 6 seconds. The Master Control Station monitors the entire GPS system. It gathers data from each monitor station, validates the information, and computes updates for each of the satellites. It then constructs a new navigational message and transmits the message to one of 3 ground antennas, which uplink the new navigational message back to the satellites. Pilots and other users of the GPS navigational data use a receiver to intercept signals from several satellites and compute their position. The low cost and high accuracy of GPS receivers is leading to rapid acceptance throughout the transportation industry and is providing aircraft with extremely precise position information.
What GPS does for pilots is it provides them with an extremely accurate navigation source at a fairly low cost, and actually takes up about the same amount of panel space as a single navigation radio that they have now for a lesser cost. So in effect, it'll replace a DME, a VOR, and anything that's needed for situational awareness.
The technology utilized by GPS is complex, but the method of determining position is easy to understand. Each satellite continuously transmits data consisting of the satellite's identification and position, the precise time, and any clock bias or error. A GPS receiver in the aircraft receives signals from several satellites simultaneously. A processor in the receiver determines the radio signal's travel time from the satellite to the receiver. The receiver then multiplies the travel time from the satellite to the receiver by the speed of light to determine the receiver's distance from the satellite. The receiver then calculates a range of possible positions relative to the position of the satellite. The receiver computes the distance from all of the satellites in view and determines its position relative to each satellite. The data processor in the receiver then determines exact position through a process called triangulation. A 2D position can be determined with 3 satellites in view. A minimum of 4 satellites is required to determine a 3-dimensional position: latitude, longitude, and altitude. The GPS receiver uses this information to provide the pilot with precise indications of latitude, longitude, altitude, and time.
GPS is much more accurate, so when a pilot flies a course line, he's normally within a mile of that course line at all times. And that stays consistent regardless of what his position is in reference to the waypoint that he's navigating to. With VOR and ADF, it's different, in that the further away you get from the nav aid, the less precise the positioning becomes.
The accuracy of GPS is better than VOR-based navigation, making it acceptable for oceanic, en route, and terminal navigation, and for non-precision approaches. However, GPS by itself is currently not accurate enough for precision approaches. Several enhancements to the basic GPS system, called differential GPS, are currently being developed to provide navigational support accurate enough for precision approaches. The Wide Area Augmentation System, called the WAAS, is an FAA system composed of 24 reference stations located throughout the U.S., each supporting an area of up to 250 nautical mile radius of the station. The reference stations receive signals from GPS satellites and determine the difference between the GPS indicated position and the surveyed position of the reference station. Corrective signals are transmitted from the reference stations to the WAAS master control stations, which validate and format the information and send it to the ground earth antenna for transmission to a communications satellite, which then transmits the information to the GPS receiver. The WAAS increases accuracy dramatically. Aircraft can calculate their position accurately to within 7 to 10 meters horizontally and 6 to 8 meters vertically.
The difference between wide area and local area differential is that the wide area system gives us accuracy necessary for Category 1 approach, but is not good enough for Category 2 and Category 3 approaches. So we need another type of augmentation system. The local area differential system does that, and will actually give us sub-meter accuracy that's necessary for Category 2 and Category 3 approaches.
Local Area Augmentation System operates in a similar manner. However, it supports a smaller area of coverage than the WAAS, about a 20 to 30 nautical mile radius of the site. Local Area Augmentation System increases horizontal and vertical position accuracy to within 3 to 5 meters. Local area augmentation also improves integrity and availability. The system continuously monitors accuracy and provides a warning when data from GPS is not accurate enough to use for navigation. Receiver Autonomous Integrity Monitoring, or RAIM, is a capability built into GPS receivers to verify the integrity of the GPS signals by determining if a satellite is transmitting corrupt information. RAIM needs at least 5 satellites in view to work, or 4 satellites and a function called baroaiding, which uses altimeter data to supplement the satellite position information. RAIM is now required in all GPS receivers certified for IFR use. The WAAS should eventually ensure 100% integrity for the GPS system. One of the strengths of the GPS system is that it is available 24 hours a day. It is unaffected by weather or terrain, and it can service an unlimited number of users. GPS will have a revolutionary effect on the national airspace system. GPS, augmented with the WAAS, should eventually provide Cat 1 capability to every runway in the U.S. at a fraction of the cost of ILS systems. This will dramatically increase landing capacity throughout the nation. GPS will allow more direct routings, resulting in substantial cost savings for the aviation industry. New, more efficient routes will be added, especially parallel routes to relieve congested existing routes. SIDS, STARS, and other standard procedures can also be redesigned to take advantage of the flexibility and accuracy of GPS capabilities. And the global coverage of GPS will enable the FAA to substantially reduce separation requirements in the oceanic environment. Controllers will also benefit from this revolution in navigational capabilities. GPS will improve the precision and safety of the entire air traffic control system. Precise position information will help improve pilot compliance with the ATC clearances. Controllers and pilots will know the exact positions of aircraft, independent of radar coverage. The creation of GPS-based approaches will increase landing capacity at airports that previously did not have approach nav aids, and will improve the accuracy and safety of approaches. Controllers can expect major improvements in the capabilities of local area airports, both big and small.
We're going to see the beginning of an evolution in the way we think about navigation. We can start designing airspace and procedures to make everything much more efficient and increase our service to the pilots.
GPS has the potential to improve safety on the ground when used as a surveillance system for aircraft and vehicles on the airport surface. And ground controllers can expect to provide unrestricted departure procedures during times of poor visibility. GPS, high accuracy, low cost, precision navigation. GPS technology will provide benefits for many, both on the ground and in the air. And as air traffic controllers, you are part of the leading edge of this revolution in technology. It's a technology whose time has arrived.